In this video, we're going to use the limit definition of the derivative, which we put right here, to find the derivative of y equals x to the 8th. So we're going to find the derivative using the longhand method, just to see how the process works in this case, and because it's the kind of question that's going to be on the exam. So as we noted before, we need to expand the binomial x plus h to the 8th using Pascal's triangle. So we're going to do that on the next blackboard. So we've drawn Pascal's triangle down to the row that gives us the coefficients for x plus h to the 8th, and we're going to use that to write the expansion of it in the limit definition of the derivative for x to the 8th. So we've expanded x plus h to the 8th, and we've got all of the terms here, and we notice first that the first term, x to the 8th, is going to cancel with the x to the 8th at the end. And let's also note the pattern that we are using to write out the terms. Obviously the coefficients are the same as those on this line of Pascal's triangle, but let's also note what happens to the powers of x and h. So notice that the powers of x go 8, 7, 6, all the way down to the power of x in this term, which is 0, and that the powers of h start at 0 in this term, and then the power is 1, 2, and they increase all the way up to h to the 8th in this term. It's also valuable to note the symmetry of Pascal's triangle. Notice the pair of 56s on either side of the 70, the pair of 28s, the pair of 8s, and the pair of 1s. And that symmetry is further in the terms themselves. So this term with the 28 that has x to the 6th h squared is symmetric with the term that has 28 that's x squared h to the 6th. See that again with the 56 x to the 5th h cubed, and the 56 x cubed x to the 5th. So we want to group these terms in the braces to take advantage of the fact that a large number of the terms can just be characterized by their power of h. So let's put a grouping symbol around those terms. So all of these terms enclosed in the square brackets can be characterized as terms which have a power of h bigger than or equal to 2. So let's rewrite our limit expression, writing all those terms that way. Now, as before, when we have a limit, we have a 0 over 0 limit, as we have in this case, which would happen if we plugged h into the numerator. All of this term right here would be 0, and all of these terms would be 0, and the denominator is 0. And you recall from when we did limits, 0 over 0 limits, our objective is to remove the h in the denominator. So we note that we can do that because h divides into all of these terms in the numerator. It removes the h from this term, and it changes all of these terms so that the power of h in them is now greater than or equal to 1 for all of them. So that cancels the h in the denominator. We no longer have a 0 over 0 limit, and we have this limit. So this is a plug-it-in type of limit because we're able to put h equals 0 into all of these terms, which will then go to 0, and what remains is this term, which doesn't have an h in it. So we get a result 8x to the 7th. Now, obviously, we could have used the power rule to get this derivative very quickly. Y. We know that y equals x to the 8th. We just bring the power down and reduce the power by 1, so we could have gotten the derivative that way, but we want to do one example of this type to show that the limit definition of the derivative can be used in combination with Pascal's triangle to find derivatives of functions to a power. So, for example, if the function was y equals x to the 6th or 7th or 9th or 11th, you should be able to use Pascal's triangle to find the limit using the limit definition in this manner. A good practice problem might be trying to find it for y equals x to the 10th. If you can do it with Pascal's triangle up to that power, then you should be able to do it for any power that would show up on an exam question.